Welcome to another numerical example related to shear center topic. Here we are seeing unequal I section. In the previous video we have seen channel section. There we have seen also the introduction for shear center. Why we need to find out the shear center. Alright. Of course we shall discuss briefly about it. Shear center is a point. If you apply the load at that point, there will be only bending, no twisting. Right, that is what we have already seen in the previous videos. We are seeing here unequal I section. For this unequal I section, if shear center may be inside or outside the any place part on x-axis, because it is symmetrical about x-axis. I have already told you, when the section is symmetrical about x and y-axis, the shear center will coincide with the centroid. If the uh, if the section is symmetric about one axis, then the shear center lies on that axis. And if it is not unsymmetrical, what happens we shall see in the next video. As of now, let us see for I section which is symmetrical about x-axis. Of course, the shear center is obviously on x-axis. And why we are finding out shear center is, if you apply this imaginary point, this is not practical, this is an imaginary point that describes about the location of load. If you could apply load at this point, there will be no twisting, there will be only bending, there will be no unsymmetrical bending then. So it will be bending, there will be no torsion twisting. This is the imaginary point that is used in design of steel structures in order to find out how much distance this shear center is located. If it is having more distance, the more torque will develop in the section. So in order to find out the location of shear center, we have to in order to describe the torque in that section, we have to consider the shear center for design of steel structure. That is about an entire thing is talking about such things what I have explained now. So you can also, this is known as center of twist. Shear center is also known as center of twist. So this is what I have already told you. One axis of symmetry, two axis of symmetry, and when load passes through the shear center, there would be only bending in the cross section and there is no twisting. So like this, this is already I have shown you in the previous video also. If the section is if the force is not applied at the shear center, then it may twist like this. If you could apply load at this shear center, there will be no twisting, only bending. That is imaginary point only. You cannot apply load over there, but it is an imagination that if you could apply over there, all the forces will be balanced and there will be only bending. So and there will be no unwanted movements that is the which cause bending. There will be only you can use m by I is equal to sigma by y is equal to E by R. In such case, if you could apply the load at the shear center, but it is not possible. In order to find out the torque in the section, we have to consider that shear center. That's it. So this is unequal I section. If you apply load like this, if you apply load anywhere, if you could not apply load at the shear center, then it will twist like this. If you could apply load at the shear center place, then it will be only bending. There will be no twisting in this. So it may bend like this. That's it. Okay. Let us see now. An unequal any equally is I section is symmetric about x and y axis. Equal I section means, so it is like this. It is symmetric about y axis. It is symmetric about x axis. And whatever we are for such type of I section, the shear center is at the center. So look, it is coinciding with the centroid. And for this unequal section, we are now calculating the shear center location. Okay, we know that the shear stress follows the direction of boundary, and hence the shear stress distribution is horizontal in flanges and vertical in web. I have already told you, as the section is I shape, the shear path will also be in the same shape, because whenever you apply some shear force on the section, that suddenly will not be applied, that will flow along the section. So from bottom to top, the flow will be like this. So here let me say S1 is a force. Uh, for this is simply two channel sections. This is one channel section and this is another channel section. These together form the unequal I section. That's it. And for this shear force, I have taken as S1 for this, and this is S2. and T1 is the thickness of flange, T2 is the thickness of web. So as similar to as channel section we are taking here, the corresponding shear forces due to these stresses will be horizontal in flanges and vertical in webs. You can see the shear flow that is horizontal in flange and vertical in web. Now, the total shear force on the web will be equal to the applied vertical shear force. So, whatever the force you apply here, that will be balanced by this force in the web. That is balanced. Okay. Now, these forces, these S1, S2 forces, and their moments are not balanced. So, we have to balance them and find out the eccentricity. That is nothing but have to find out location of shear center. And here the vertical force is balanced, but the shear forces in the flanges are unbalanced. These S1 and S2 are unbalanced. They are equal and opposite and hence produce couple as shown in the figure. They are producing couple moment. The unequal section shown in the figure is symmetrical about x-axis and hence shear center will lie on this axis. So this is x-axis. It is symmetrical about that axis. So location will also be on x-axis. So let me consider here. Let us take T1 is the thickness of flange. Okay, T2 is the thickness of web. Here S1 is shear force in shorter length of the top length. Shorter length. Let me say shorter length shear force. And S2 is shear force in longer length flange. This one, longer length. In order to identify them, I'm telling them as shorter and longer. So you can put whatever notations you want. The only thing is you have to understand. Now, if you remember again, let me do that. Tau is equal to FA bar by IB. If you remember from the previous semesters, the shear stress expression can be this, right? So we are using that formula here. And here let me substitute whatever the values we have. F is applied shear force we have, and area we are considering a small element here, right? So that is small x into T1. And y bar will be distance up to the center, this one, that is h by 2, simply this one, h by 2. Now I is moment of inertia about x-axis because we are considering the only one x-axis, and this is distance from the x-axis, right? Then b will be the width of, so the flow will be like this. So consider this element as this, like this, and it is having this one as, this is b, this is width actually, so that is thickness. So I have rotated it like this 90 degrees, so that it is the figure exactly here, right? So then I consider here b for this particular section. B will be width, that means this thickness will be the width, T1. So let me substitute all of them here. What will you get? Tau is equal to f into x into T1 into y bar is h by 2 by ixx into T1. So T1 will be cancelled, fx h by 2 ixx, that will be tau. Take it as equation number 2. Now let us find out shear force in this elementary area, this part. Now what will you get? Shear force in elementary area, let me say ds is equal to tau into dA, because tau is shear force. So yes, we are considering it as shear force by area. Force stress is force by area, then force is stress into area. Simple concept over here. So in order to find out everything, okay, let me substitute tau here. Before that, we have is f let me fh by fxh by 2ixx, fxh by 2ixx into dA. So that is what we have ds value. So in order to find out for entire this flange up to here at the part up to b2, so let me uh, put the points over here, let me give the limits over here. What I get is, and one more thing here, one more thing about fxh by 2ixx, and dA is a small part here, dA this part, so that will be dx multiplied by t1, this rectangle, small rectangle, dx into t1, that will be now f into h t1 by 2 I xx into x dx, that is ds. So now let us find out top flange, longer flange, that s1 s2, right? Longer flange will be s2 here, s2 will be integral ds, and limits are from where? From s2 is spreading from this here to here, so I said from 0 to b2, 0 to b2, that will be from 0 to b2 f h t1 by 2 I xx into x dx. Now take out all the constants outside, f h t1 by 2 I xx integral 0 to b2 x dx. So in the next step I will write it as integral 0 to b2, sorry, f h t by I xx, f h t1 by 2 I xx into this is what we have, x dx. So let us apply integration. So what will I get? F h t1 by 2 I xx into x square by 2, limits are from 0 to b2, b2. Now f h t1 by 2 I xx into b2 square by 2 minus 0 square by 2. So ultimately that is f h t1 b square by 4 I xx, that is s1. Okay, now take it as equation number 4, s2, right? Sorry, s2, s2. Now similarly in the same way, if you apply this, if you apply limits for the same equation, if you apply limits of 0 to from b1, limits are from 0 to b1, you will get s1 value. Same will be occurred, s1 is equal to, similarly, and this s1 calculation is given in notes, please download it and see. FHT2 in the place of, sorry, FT1, right? This is the thickness of flange is similar T1, sorry for that, T1, T1, this is B2 and this is B1 square by 4IXX. Take it as equation number 5. So we have S1 value and S2 value. Now let us find out E. Let us now find out E. Take before that, let us take moments about point O. Moments about point O. So what we have here, S1 into h by 2, s1 into h by 2, that is anti-clockwise moment, same minus s1 into h by 2. So anti-clockwise I am taking here minus, clockwise I am taking as positive, or you can take them in in reverse also, no issues. Okay, s1 into h by 2, so here also s1 into h by 2 from bottom, so that is also anti-clockwise moment, s1 into h by 2 minus s1 into h by 2, and this is there s2 into h by 2, that is clockwise, so I'll put it as plus s2 into h by 2. Here also it is there s2 into h by 2, that is also, sorry, s2 into h by 2, that is also clockwise, plus s2 into h by 2, and one more thing is there, that is again anti-clockwise, minus f into e, minus f into e is equal to 0. Sum of moments about point O are 0. Now what will I get? I will write it as minus s1 into h by 2, h by 2 will be h, plus s2 into h minus fe is equal to 0. So I will write it as s2 minus s1 into h is equal to f into e. Now I will write it as e is equal to s2 minus s1 into h. So what is s2? We have already found in the previous slide, s2, s1 values. Let us substitute them here. So e will be equal to s2 value f into fht1 b2 square by 4ixx minus fht1 b1 square by 4ixx into h by, okay, that's it. Okay, by f I forgot to mention, f by f, right. So now I will take common fht1 by 4ixx, right. I will take common, what is remaining, b2 square minus b1 square into h by f. Now I will write the final equation as, so let me write it here itself. You can better see it here, is equal to fht1 by I 4ixx, this h I will put it here, f h square, fh square t1 by I 4ixx into b2 square minus b1 square. So if you substitute this, you will get very simply the shear center location, but you have to learn this derivation for exam point of view. Let us solve the simple question of it. Determine the position of shear center for channel section. Sorry, I forgot. Yes, I forgot to remove channel section here. Okay, determine the position of shear center for I section of unequal, okay, unequal I section as shown in the figure. Let me draw the figure here that is actually given in the question. Now let me draw it here. This is unequal I section we have. Please adjust. The edges are not very sharp. Okay. Now this is x axis. This is 30 mm. This is 40 mm. The entire thing is this 150 mm, and the thickness we have 20 mm. This is 10 mm. This is 20 mm. This is also 20 mm. So this will be 150 minus 20 minus 20, 110 mm. So this is the question we have. Now we have to find out. Initially I said shear center has nothing to do with the load which was applied on it, but this is only focusing on the shape and size of the section we have. So let us write the data what we have from the question. So before that, let me mark the shear force flow here. So this is how it is going. This will be Fw. So we have to consider this as S1 and S2. Let me put it for the longer side, S2. Okay. Now from this diagram, the data we can write it as B1 is equal to 30 mm, B2 is equal to, this is 40 mm, H is equal to, H means this part, S1 to S2 gap, sorry, S1 to S1 gap, top flange to bottom flange, that will be 150 total distance minus this thickness by 2 and this thickness by 2, 20 by 2 minus 20 by 2, that will be 150 minus 20, that will be 130 mm. Thickness 1, that is the thickness of flange, is given as 20 mm, and thickness of web T2 we have 10 mm. So this is what the data we have, and we can easily now find out the shear center, but only thing we need to have moment of inertia Ixx. For this, let me say 2 into B1 D1 cube by 12 plus B1 D1, that is area, into y bar minus y1 whole square, plus for web simply I will write it as B2 D2 cube by 12. B2 D2 cube by 12. So where, let me mark here what is B1 B2, what is D1 D2. This entire thing is B1 and this is small d1. This is sorry, d2. This is d1. Okay, just a minute. So this b1 d1 for the flange. Okay, this is d2 up to here. Again this also comes under d1. D1 for flange, d2 for web. Please don't get confused here. This is b2. B2 is the width of the flange, B1 is B2 is width of the web, B1 is width of the flange. D1 is depth of the flange, D2 is depth of the web. So let me substitute all the parameters here. So if you have B1 will be this entire value the values are clearly written in notes. Okay, let me otherwise write it here. B1 is 70, B2 is 10, B2 is 10, D1 is 20, D2 is 110, Y bar will be 150 by 2 here, this one, and Y1 will be D1 by 2, that will be 20 by 2, 10 mm. Now if you substitute all the values which are available, all the values here, all are available. If you substitute, then you will get the value as moment of inertia 130,32500 mm power 4. So that substitution and calculation was clearly given in the question, and simply you have to know what are the parameters I have or I am about to substitute over here. Now you can find out the position of shear center. What is the formula for this position of shear center for an equal I section will be h square into t1 multiplied by b2 square minus p1 square by 4ixx. Let me substitute all the values here. H square, as I remember, we have 130 square into thickness. Now previously thickness of flange we have 20 mm multiplied by b2 will be 40 mm square, 30 m square by 4 into ixx, that will be 130,32500. So if you do that, you will get 4.538 mm. So that means for this I section, this is 10 mm, right? 10 mm. If you locate the I section, say shear center, if it is the central axis for the web, this will be at the distance of 4.58. Have you observed this is inside the section? The shear center is located inside the section over here. So that means it is subjected to very less torque whatever the load you apply on this. Whatever the load you apply on this, it is subjected to less torque. If the shear center is away from the axis, then you'll get more torque. Then it has to follow separate design considerations while designing some steel structures in design of steel. So that will entirely design of steel structures that you will see in your next semesters. That will be very interesting if you know this concept. Please practice this and do this homework. This is also very simple. If you substitute whatever the values I have done, you can simply do it very simply. Determine the position of shear center for an unequal I section as shown in the figure. I have not given you figure. Let me draw it here. This is unequal I section we have, and this is 60 mm, that is b1 is 60 mm, and this is 80 mm, that is b2. This thickness of flange is t1 is 40 mm, and this entirely this is 300 mm entire depth, and these are also same values as below. This is also 60 mm, this is also 80 mm, and thickness of web is 20 mm. Yes, you do this and send it to my mail id, and if you have any doubts you can contact me through this. Now locate the shear center and imagine where if you apply the load at the shear center, then it is not subjected to any twisting other than bending. It is subjected to only bending. Now you can use the bending equation. That is like pure bending. When it is there is no twist, there is no shear force, that will be under pure bending. That pure bending theory can be applicable over there. So that's the only criteria we use shear center. That is, this might be the almost last concept, or in other videos subsequently we shall see other remaining sections and what are the criteria we have to consider for shear sections for difficult sections, if it is possible. Otherwise, I will share the document with you people. Thanks for watching. Please do the homework and send it to me.